In this video, we will walk through examples of how to calculate mean, median, and mode using Excel commands. Mean, median, and mode are three common measures of central tendency. In this file, we have a set of 11 data points, and the first thing that we're going to do is find the mean, or the average, of these values. Put your cursor below the bottom of the set of values and type equal average. When you type the open parenthesis, it will guide you through the rest of what goes inside the formula, which is the set of numbers we'd like the average for. With the cursor, I'll select the 11 data points here, and then close parenthesis, enter, and it tells me the average of this set of data is 52. I can also find the average using the sum on the Home tab. Here, click the drop-down next to it and say Average. Excel will do its best to guess what data points you want to include. Click OK if you accept the data set which has been captured inside the parentheses, or modify it as necessary, and click Enter. Again, the average is 52. Let's identify that as the mean. Now let's do the median. The median is the value which is in the middle of your data points. Equal median is the formula. Open parenthesis. Select the data that you'd like to get the median for. Close parenthesis. Enter. And the median value is 53. The mode is the most frequently occurring value in our data set. If your data has more than one mode, be aware that the mode formula will only find the first most frequently occurring point in your data. The formula is equal mode, open parenthesis, select your data points, close, and as you can see, it tells us 49 is the mode. However, as we look at our data, you can see that 49, 54, and 55 all occur twice, meaning that we have three modes in this data set. Excel has an array function called mode.mult, which will allow you to return multiple modes from a data set. In this case, we know there are three modes. Let's select three blank cells and type equals mode.mult, open parenthesis, select the data, close parenthesis. Instead of hitting enter, however, Control-Shift-Enter is the command we need to use. Notice that on the formula bar, we have now got curly brackets around our formula, and we have returned three values in the cells we had selected. This is mode.mult, an array formula in Excel which allows us to identify more than one mode in a data set. This formula will allow you to select multiple rows and columns and then have the output appear in several blank cells. If our dataset had only two modes and we had selected three blank cells for the mode.mult output, the third cell would repeat the first mode. If we only had one mode, then it would be repeated in all three blank cells. Mode.mult is useful for datasets which may have multiple frequently occurring data points. In this video, we have demonstrated how to calculate three measures of central tendency using formulas in Excel: mean using the average formula, median using the median formula, and mode using both mode and mode.mult formulas. This video will demonstrate how to calculate a weighted mean, also known as a weighted average, using the sum product formula in Excel. There are times when it is helpful to weight a set of data before taking the average. The data set may be composed of similar items which have different valuations, and taking a simple average does not suffice. In this data set, for example, we have 12 homes represented. The size column is thousands of square feet per home sold. 1.4, therefore, is a 1,400 square foot home. The selling price is also in thousands, which means that the 1,400 square foot home sold for $100,000. If we'd like to understand the average selling price per square foot, it would be helpful if we first found the total amount of dollars spent by the total amount of square footage, and then got the average so that we have a weighted average per square foot. We can easily do this by calculating the weighted mean in Excel. I'll demonstrate with the longer method and then show how it can be done using sum product. First, we need to add a new column. Column C we'll call size by selling price. And for this column, we're going to multiply size times selling price. I want to do that all the way down the column. Now that I've got the first formula in, double click and it will carry my formula down the column. Now I sum that column using on the Home tab this sum feature, and I also need to sum the size column. Now to get the weighted mean, I need to divide my size by selling price total by the total number of square feet. All of these are in thousands, and the final number I get will be dollars per square foot. My weighted mean is 1344 divided by 13.8, which is about $97 per square foot. Now let's look at how we do this using sum product. Sum product will do for us what we did in column C. It will multiply size by selling price all the way down the two columns and add the resulting products together. Equals sum product, open parenthesis. Notice it's telling us that we need to use an array here. That simply means that we're going to be performing operations on multiple rows or multiple columns rather than individual cells. So I've captured the size column. Now I'll capture the selling price column, close parenthesis, enter, and you can see that the result, 1344, matches what we had already found to get the weighted mean, divide it by 13.8, and we have the same result. Our weighted mean is $97.39 per square foot. Another common use for a weighted mean is to calculate the grades for a class. In this table, you can see points earned by a hypothetical student for various assignments and the weight for each graded item. For example, the first 3 exams are worth 10% each for the final grade, and the final is 25%. The project is 20% and homework totals 25%. That gives us the 100% total bucket of points. All of the assignments have been scored out of 100 points. If we only add the raw points up and divide it by 1,000, then the student would have a score of 80.1%. That's their raw score here. However, when we assign weights, giving more weight to the exam scores and to the project than the homework, the student's score drops to a 76%. This is a second use, therefore, of a weighted average. Sum product has been used here to multiply points times weight all the way down the columns, and then divided by 100, indicating that we now have a weight out of 100%. When we divide the total number by 100, we get 0.76 or 76%. Two cautions with sum product. All data must either be in rows or in columns. We cannot mix and match rows with columns. And both rows or both columns must have the same number of data values. If those two criteria are met, sum product is a useful tool for quickly summing the product of two data ranges, and from there calculating the weighted average. In this video, we will use Excel's Geo Mean function to compute the geometric mean of a set of numbers. The geometric mean is useful for finding the average growth rate while taking into account the effect of compounding. It is often applied to percentages, ratios, indexes, or growth rates over time. Let's consider this data set, which represents the percent increase in sales year over year for a company for the last 5 years. Here you see two scenarios. In the first scenario, year-over-year increases were positive each of the 5 years. In the second scenario, one of the years had a sales reduction from 2010 to 2011. We will use the Geo Mean function to determine the geometric mean percent increase over this 5-year period. Note that all numbers are in decimal format representing percentages. 0.094, for example, is 9.4%. That translates to, in 2010, sales increased 9.4% over 2009 sales, and sales increased 13.8% from 2010 to 2011. In the second example, sales decreased 13.8% from 2010 to 2011. That does not mean that sales were negative. It means that sales revenue in 2011 was 86.2% of 2010's sales revenues. The numbers greater than 1 in columns C and G represent years in which sales increased year over year, and less than 1 represents a decrease over the prior year's revenue. All values in a geometric mean must be positive. That is the reason that we add a 1 to the percent change to take care of any negative changes from period to period. Now we're ready to find the geometric mean. The geometric mean formula is simple to apply once your numbers are ready. Equals Geo Mean, open parenthesis, and then select the values that you want to have inside the formula, close parenthesis. Here you get a number that is greater than 1, indicating that we had an overall increase during this time period. That value means 112% approximately as our geometric mean change over time. We will typically subtract 1 from this result in order to put it into a percent format. In other words, when we subtract 1, we'll have 12.3% is our geometric mean change. Let's look at how we calculate this formula using the textbook version of the formula, and that will give us the exact same result. The manual formulation is to take each of the values in column C and then raise it to 1 over 5, the 5th root of the values, and you get the exact same result. We'll subtract 1 from the geometric mean result in order to see our percent change per year. In the second scenario, we see that because of the negative value in one of the years, our Geo Mean is less than it is in the first scenario, as it should be. That negative 13.8% change in sales will have a reducing effect on our average over time. As it did in the previous example, the manual formulation will have the same result, and subtracting 1 from the result will show us that we have a geometric average of 6.2% change. Using the geometric mean allows us to take into account that the change in sales is based on a cumulative change. When we report an increase of 9.4% from 2010 to 2011, the new sales base is then used to report an increase or decrease of 13.8% for the next year's total sales. In this video, we have walked through an example of how to use the geometric mean to show the geometric mean change for year-over-year sales. In this video, we will use Excel's max and min functions to find the range in a data set. Range is a measure of dispersion. It shows the distance between the largest and smallest value in a data set. This data set shows 13 years of annual revenue for domestic sales, international sales, total sales, and it also shows the number of employees that a company has for those 13 years. Excel does not have a range formula. Instead, we calculate range by finding the largest number in a data set and subtracting from it the smallest number in that data set. The Excel function to find the largest value is max. For the smallest value, we use min. We could do the entire calculation in a single cell, but for clarity, I'm splitting it into 3 cells, one each for max, min, and range. In the max cell, type equal max open parentheses, and then select the cells which you would like to include in your data range. Close parenthesis, enter, and you have the max value in that set of data. Next, we will repeat the process using min. We see that our max is 34,066,000,000, and our min is 17,829,000,000. Our range is the difference between the two. Our range is 16,237,000,000. We can then repeat this process by dragging our formula across the cells, and we can actually drag several at the same time, and it will copy the formulas that are in the original cells across the row. We go ahead and bold these to make it easier to differentiate our data from our results. We see that the range is 16.2 billion for domestic sales, 25.8 billion for international. The total is 40.9. And then when we look at employees, we have a range of 23,000 between the largest and the smallest number of employees that have been employed over those 13 years. Note that range is not telling us anything about the growth in sales from start to finish or the growth in employees from start to finish. It is simply telling us how large the difference is between whatever value is largest and whatever is smallest in a data set. In this video, we have demonstrated how to calculate range in Excel using the max and min functions. In this video, we will calculate the variance and standard deviation for a population using the var.p and stdev.p functions in Excel. A population consists of all the values that fit a certain characteristic we care about. For example, we might collect all of the final exam scores in one particular section for one semester of a statistics course. If we only care about the final exam score, and only for that particular section and semester, then our data set is a population. If we then selected 5 values from that population, those 5 values would be a sample. Here we have a data set that is considered a population because we have all of the annual sales for all 13 years a company has been in business. Variance and standard deviation are 2 measures of dispersion. They provide information about how far data vary around the mean. The 2 measures are related. Variance is the square of standard deviation, or in other words, standard deviation is the square root of variance. The formulas to calculate variance and standard deviation are slightly different for a population than for a sample. Excel does the heavy lifting and allows us to identify whether we are calculating sigma and sigma squared for a population or for a sample. In this case, we have a population. First, let's calculate variance. Let me demonstrate the difference between 2 of the formulas in Excel. The Var formula is actually variance for a sample, equals var, and select the values I want to include, close. It returns quite a large number. However, when we put var.p, indicating that we are using a population, notice that while it is still a large number, it is smaller than the first number we've calculated. That is because the variance of a population will typically be smaller than the variance for a sample. We want to use var.p in Excel when we know that we have a population. The same thing is true with standard deviation, which I'm going to put here as SD, equals stdev. Note that you have some choices in Excel. stdev.p means for a population, .s for a sample. I'm going to put .p. Now I'll select my numbers, and I see that my standard deviation for the population is 4.6 billion. Recall that I said that standard deviation is the square root of variance. Let's check that out. And you can see that we get exactly the same result. When I take the square root of variance, I get the same number as I get in my standard deviation formula. Now I'll drag these across. This 1.76 plus means that it's quite a large number. We don't have enough space in our column, so I will make the column larger. We have now calculated standard deviation and variance for this population of 13 years of sales and employment for a company by dragging the formula across the rows. Only use stdev.p and var.p when you are sure your data set is a population. Otherwise, use the formulas which assume the data are a sample. In this video, we have demonstrated how to calculate variance and standard deviation for a population. In this video, we will calculate the variance and standard deviation for a sample using the var.s and stdev.s functions in Excel. A sample is a subset of values drawn from a population. Here, we have a sample of homes sold in a city for a certain month. The size column is the number of square foot per home, and the selling price is the price that the house sold for. Variance and standard deviation are two measures of dispersion. They provide information about how far data vary around the mean. The two measures are related. Variance is the square of standard deviation, or in other words, standard deviation is the square root of variance. The formulas to calculate variance and standard deviation are slightly different for a population than for a sample. Excel does the heavy lifting and allows us to identify whether we are calculating variance and standard deviation for a population or a sample. In this case, we have a sample. I'm going to first identify the variance, and the formula is var.s, and then I'll select the values I'd like to include. And the variance is a large number. This would be 35,454 square feet. I'm going to drag it over and have it calculate the variance for my selling price. The standard deviation, as you can see, you have choices for the formulas. The .s indicates that you're getting the standard deviation for a sample, is the square root of the number we just found. In the first case, we have 188 square feet as the standard deviation for the size of the homes which sold in this sample. As I noted, standard deviation is the square root of variance. If I take the square root of variance, I'll have exactly the same number as when I used the formula for stdev. In this video, we have demonstrated how to calculate variance and standard deviation for a sample. In this video, you will learn how to use the output from the Descriptive Statistics tool to find measures of central tendency and dispersion in a sample. Our data set is a sample of 16 households with landlines for phone service in a large city. We see here the number of phone calls made per household during the first week of July. We're going to use the Data Analysis menu to generate descriptive statistics about our data. In the Data tab, click on Data Analysis. Once you open Data Analysis, scroll to Descriptive Statistics and click OK. In Descriptive Statistics, input range is the set of cells you want to analyze. Click inside the input range box, then click the top of the column for A. Because we've included our label, we'll click Labels in First Row. By default, it's set for New Worksheet Ply, which means that output would be stored in a new worksheet, but I'll go ahead and have it stored in this worksheet. Click on C2 or whatever cell you'd like to have your table appear in. Click Summary Statistics and click OK. I'll increase the width of the column so that we can see the labels. Our table has calls at the top because we chose to include the label in our output. This table has a lot of useful information. Let's mention 8 items, 3 measures of central tendency, mean, median, and mode, and 3 measures of dispersion, standard deviation, sample variance, and range. We'll also reference minimum and maximum. Mean is the average of your data. Median is the midpoint of the data. Mode is the most frequently occurring value. One caution is that descriptive statistics will only find the first mode in your data. If your data are multimodal, you will not see that in descriptive statistics. For example, if we sort our data set, we can see that there are 2 modes because 2 values occur twice, 30 and 46. Descriptive Statistics only found 30 as the mode. If you believe your data are multimodal, and you need to know both of the modes or all of the modes, don't rely on descriptive statistics for this bit of information. You can use the mode.mult formula. Measures of dispersion include standard deviation, variance, and range. The standard deviation for this sample is 12.8. The mean is 34.1. The standard deviation is nearly a third of the mean, which tells me there's quite a bit of variation around the mean. Variance is the square of standard deviation. Note that descriptive statistics always assumes your data set is a sample. If your data set is a population, then descriptive statistics will not perform the calculation you need. Range is the difference between the minimum and maximum values in your data. As you can see, the range of 47 is the difference between 52 and 5, the largest and smallest values in our data set. In this video, we have demonstrated how to generate descriptive statistics and how to identify measures of central tendency and dispersion in the output. In this video, you will learn how to compute the arithmetic mean and standard deviation of grouped data, or in other words, how to determine the mean and standard deviation of data displayed in a frequency distribution. Here we have a frequency distribution showing how many clients are represented by 50 small public accounting firms, each with 10 or fewer employees in the Dallas-Fort Worth area. What if we wanted to know the average number of clients represented by small public accounting firms? In that case, we need to calculate the arithmetic mean of our grouped data. We're going to multiply the midpoint of each class by the frequency of that class to get a weighted total for that class. First, we begin by finding the midpoint. Finding the midpoint requires averaging the lower bound of two consecutive classes. In this case, we would average 20 and 30. So we'll take 20 plus 30 divided by 2, and we get a midpoint of 25. We'll repeat that with the next class to find its midpoint, and we find that its midpoint is 30 plus 40 over 2, or 35. As you can see, the width of each class is 10, which means the width between midpoints will also be 10. I'll set up a simple formula and drag it the rest of the way down the column. You could also simply enter the exact numbers, but I'll go ahead and create it as a formula. I've set up C3 plus 10 as the midpoint for my third class and dragged it down the column so that it iterates 10 units per midpoint. Now I can use the sum product formula to have Excel multiply the midpoint times the frequency and add the results from each row all the way down the column. Then I'll divide by the total number of items in my sample. That will be the arithmetic mean. Let's go ahead and do that in this cell. Equals sum product, and I'll select the frequency, put a comma, and the midpoint, and now Excel is going to multiply and then sum all the way down the column. That's the numerator of my formula for arithmetic mean for grouped data. I'll divide it by the total of the frequency column, and now I've found the arithmetic mean of my grouped data. On average, 44.8 clients are represented by small public accounting firms in this sample of 50 such firms from the Dallas-Fort Worth area. To calculate the standard deviation is a tiny bit more complicated, but Excel makes it easy. We're first going to add a column to get the numerator of the formula shown here. We're going to take the sum of frequency times the squared value of midpoint minus x bar, or midpoint minus arithmetic mean. That's what M stands for as midpoint, F stands for frequency, and x bar is our arithmetic mean. Equals frequency times parenthesis midpoint minus x bar. And I'm going to lock the cells with the F4 key, and then I will square it. And that's what this little upper caret does, is allows you to put an exponent after it so that we can square or cube or whatever value. Now that I have it set up, I'll drag it down the column. In the standard deviation cell here, I'm going to finish out my formula. I'll take the square root of the sum of column E divided by n minus 1. This is my n minus 1. And my standard deviation is 9.4. In this video, we have calculated the arithmetic mean and standard deviation for grouped data, that is, for data summarized in a frequency distribution. This video demonstrates how to use Excel's Descriptive Statistics output to determine whether a set of data is normally distributed, and for normally distributed data, how to use the output to determine the upper and lower limits, which will capture 68%, 95%, and 99.7% of the data. In this data set, we have the blood glucose readings from February for a person recently diagnosed with type 2 diabetes. We can quickly determine if the data are normally distributed, that is, if they are symmetrically distributed around the mean, by running the Descriptive Statistics feature in Excel. Go to the Data tab, click on Data Analysis, and choose Descriptive Statistics. Click OK. Put your cursor in the input range and then choose column A. I'll select Labels in first row since reading was included in the values I captured. And I'd like to have my output be on this spreadsheet rather than on a new worksheet. I'll select Summary Statistics and click OK. And I'll widen the column so that we can see everything. Note that the mean and the median are very close to one another. The mean is 112.86. The median is 112. The closer these two values are, the more symmetric our data tends to be. Data that are perfectly normally distributed will have a mean equal to the median equal to the mode. But we can still apply the empirical rule if our data have some small amount of variation. The empirical rule states that given normally distributed data, 68% of the results will be within one standard deviation of the mean. Approximately 95% will be within two standard deviations of the mean, and 99.7%, or virtually all of the data, will be within three standard deviations of the mean. We can use the results from our Descriptive Statistics table to calculate these 68%, 95%, and 99.7% limits by using the mean and the standard deviation. I've set up a table in which I'll put the output of those calculations. For one standard deviation, it will be the mean minus the standard deviation. And for the upper limit, it will be the mean plus one standard deviation. I've finished filling in the table. For the 2 standard deviation lower limit, it will be the mean minus 2 times the standard deviation, and for the upper, it will be the mean plus 2 times standard deviation. For the lower limit, it will be mean minus 3 times standard deviation, and for the upper limit, it will be the mean plus 3 times standard deviation. Recall that I mentioned in the empirical rule, 68% of our data are within one standard deviation, 95% within two. Let's sort our data, smallest to largest. We can see the smallest value is 96, which we can also see in our Descriptive Statistics table, and the largest value is 127. If you look at the lower and upper limits we've calculated, 96 is just outside of our 2 standard deviation limit. It fits within 3 standard deviations. Our maximum value of 127 fits within the upper limit. So as you can see here, this data is not that far dispersed around the mean. Virtually all values fit within 2 standard deviations. In this video, you have seen how to use Excel's Descriptive Statistics output to determine whether data are normally distributed by comparing the mean with the median, and for normally distributed data, how the empirical rule describes the percent of data within 1, 2, and 3 standard deviations of the mean.